Thank you very much, Maria, for the nice introduction. And actually, the work that I'm going to present today is collaborative work between Polytechnico di Milano and Ghent University with research group of Professor Nelly De Belli. And I want to acknowledge also the collaboration of my colleagues and former and current PhD students. So as a matter of fact, we are dealing with sustainability, we are dealing with sustainable development goals, and you can see those going from 7 to 12, more or less, are the ones on which our job as civil engineers, structural engineers has to focus. And which is the scenario in which we are going to work. This is in Rio de Janeiro, is the Museum of Tomorrow, but this tomorrow is probably already here, already now, and we have to cope with that. We have to cope with the fact that nowadays more than half of the population in the world lives in cities. So this means that we do not only need buildings, but we need transportation infrastructure for these people to go from places where they live to places where they work for leisure time and so on. And this actually requires concrete, requires even more and more concrete volumes to be produced, because we do not have alternatives to concrete if we want to build in a sustainable way. But what we have to do? Well, we have to decarbonize the cement production. We have to reduce the cement in concrete, trying to find other alternative ways to make our concrete, and to reduce concrete in buildings. This also means that we need to look to other performances that so far we have not looked at in detail, but we also need to find the metrics to evaluate this performance. If we go for ultra-high performance concrete, for example, and only look at the content of cement per cubic meter, we will say that any high performance concrete, any high strength concrete is not sustainable because it contains more cement per cubic meter than ordinary concrete. But if we look at the efficiency of this binder and this cement in getting the strength, we can say that probably if we look at the kilos per cubic meter per unit megapascal of strength, then ultra high performance concrete is more sustainable. So change the perspective. And which are the fields in which we have to intervene? In the construction and maintenance of transportation infrastructure. This is our daily life when we have to cope with traffic interruptions and long queues on the highways, if we have to go to work or if we have to go to the beach during summer on holidays and so on. The transportation infrastructures, this is a harbor in the Mediterranean, Haifa in Israel, the first harbor where the ships, after going out of the Suez Canal, they stop for. So this is a huge port where freight ships longer than 400 meters have to arrive. So big construction project to redevelop, to enlarge, to strengthen. And can you imagine the structural demand that you have? It can look a very simple structure, it's just a concrete pavement there, but it's seaside, there are huge loads coming from the machineries and also the ships that can go on. We have to deal with coastal protection against climate accidents, against climate extreme events. This is becoming a huger and huger problem all over the world. And we have to contribute to decarbonize our energy supply, because this is the true bottleneck. Every time, if we can make our production very efficient, but depends on where we take out the power for that production, it makes the carbon footprint higher. So we must invest in renewables, and concrete is the material to be if we want, for example, to go higher with wind energy harvesting, or if we want to go deeper with geothermal drilling. And all these cases, the material are subjected to very severe chloride attack, sulfates attack, very severe structural demanding conditions for which the current code prescriptions are absolutely inadequate. You look in the codes, and for durability, for chlorides, you find maximum water cement ratio, minimum cement content, that any kind of modern concrete can easily cope with and easily fulfill. So where is the driver for innovation that the codes can provide with this? So this is the scenario in which, with a consortium of European partners, we applied for funding to the European Commission some years ago. We got funded this project with a consortium of 14 partners throughout Europe, 8 countries, I had the privilege to coordinate them. There were 5 other research institutions and, you know, consortium of industrial partners which encompassed the whole value chain of Concrete Institute, from producers of constituents to precast companies to large-scale infrastructure construction companies, up to very end users. We have here, sorry, the pointer does not work. Enel Green Power is an energy-producing company. They do not make concrete, they do not sell, they buy to build their infrastructure. So their interest was at the very last segment of the scale of the end users. And after this project, we applied with some partners as well for an international training network in which we tried to bring the innovation that we developed in the project also into education and scale up to the market. And this project is now running. We worked at the 3 levels: the product, the process, the context, and started from something which was already in the labs throughout the world: ultra-high-performance concrete. The ultra-high-performance concrete, sometimes you find probably not a complete message to deliver it. You find only a message on very high compressive strength, 150, 180, 200 megapascal, that when you go to structural design, you never use that, because a column cannot be made smaller than a certain size, because it's not a matter of strength, but then it's a matter of buckling. And if you have a beam, the tensile part dominates. So what we wanted to see was the strain hardening capacity in tension and the durability in the cracked state, which was what was matter. We achieved the strain hardening capacity. You can see there we have a strength of about 7 to 8 megapascal, but the strain hardening response up to 0.5% deformation, which is well beyond the yielding of conventional steel in reinforced concrete structures. Then our problem was, first of all, to scale up, casting half a cubic meter per hour on the construction site. So we had a batching plant there because we wanted to develop full-scale application. And now these 6 structures are throughout Europe, as you can see there: Italy, Spain, Ireland, and Malta. So this is the Italian pilot in which we used some nano-functionalized UHPC. The farthest part of it, it's a basin for sulfate-rich water. The fastest part of it, you can see there, I don't know if you see the pointer, no, and this does not work. Okay. Pointer does work, okay. Okay, so probably. Let me see. Yeah, should be this.
No, it's
lateral pointer. Okay, got it.
Yeah.
Okay, it's this one. So if you see this is ordinary reinforced concrete solution, 10 centimeter thick with about 100 kilos per cubic meter of reinforcement. You go with our nano-functionalized materials and go, if you design the wall as a cantilever 6 centimeter thick, if you design the wall like a slab supported by columns, you go to 3 centimeter thick, with a significant saving in material usage. And this is a proof that, okay, it can take water with 3 centimeter thick. The first load test, we were a little bit concerned. We stayed up front in order to stay safe, but it worked very well. This is to show the importance of the matrix. If you look at the dosage, you look at the mix design here. You say you have 600 kilos per cubic meter of cement. This mix is not sustainable. But look here, 10 centimeter thick with 350 kilos, you use 35 kilos per square meter of wall. In our case, with 3 centimeter thickness, you just use 18 kilos of cement per square meter of wall. So let's look at the functional unit and not at the unit volume of material or unit weight. Then, as I said, we wanted to strengthen the durability in the cracked state. We wanted to enhance the self-healing capacity, and we investigated the use of different kind of nanomaterials: alumina nanofibers, cellulose nanofibrils, and cellulose nanocrystals. You can see here some of the characteristics of the materials we used. For the nanofibers, we had lengths between 100 and 900 nanometers and diameters in the range of 10 nanometers. Similar dimensions, a little bit shorter, but the diameter was still in tens of nanometers for the nanocrystals and the nanofibrils. We characterized the mechanical performance of the material through bending tests and indirect tension tests. And what we get, interestingly, was if you look at we have a 4-point bending test, so you can imagine that in the central part of the beam, you have multiple cracking. And this is the key of this material. Multiple cracks, each one is very, very narrow, very tightly open, and it's good for durability. With the reference material, the average number of cracks was 7, ranging between 2 and 12 according to the specimen. When we added up alumina nanofibers, we had much more fibers in same zone, which were tighter spaced. So this was the strengthening at the very molecular level, I would say, which allowed us to obtain very, very narrow cracks. So then we wanted to explore, as I said, the durability and the self-filling capacity. So what we did with the specimens, we pre-cracked them up to the service design level. We kept healing for 1 month in geothermal water, chloride water, different curing environments. After 1 month, we tested to failure some of the specimens to see the evolution of the performance, but some other ones were simply re-cracked and put back to heal. And after 2 further months, re-cracked and put back to heal, and this went up to 6 months or 1 year in some cases. And see here the results of the crack sealing, because we expected the cracks as they were going to close. For the mix with alumina nanofibers as compared to the reference, which is the green, you see we always have a better capacity, and we always have very, very narrow cracks. And also with nanocellulose, we were able to keep the cracks very narrowly open and have an improved self-filling capacity. This was not only on the closure of the cracks, we could also see on the capacity to recover the damage. We intended the capacity to recover the stiffness, the flexural stiffness that we evaluated from this cracking and re-cracking test. And you can see here that the mix with alumina is here, and the mix with nanocellulose are the yellow ones, where the reference is here with less performance and wider cracks. Also for the capacity to retain the stress, which is an important design parameter, you see that alumina nanofibers, you are in the range of 100%, means that you completely healed and got back the same performance as for the virgin material. And some images here showing, you can see clearly here one nanofiber, alumina nanofiber crossing this crystalline structure which was formed. The nanofibers also help, but they are hydrophilic, they capture hydration, they foster the hydration of the cement, and this is in geothermal water. And some images also on how the cellulose nanocrystals, the cellular nanofibrils, really acted as nucleation site for the hydration of cement. So then we went up to scale and design a real structure. This is a basin in a geothermal power plant located in Tuscany. So you can see that it's about 20 meter by 5 meter, and the 8 of the walls are here. On one side you have about 5 meter deep, and on the other side you have 3 meter. On the 3 meter side you can access also with vehicles and machinery for the maintenance. So the original reinforced concrete design solution has a wall which is 400 millimeter thick with very deep cover, because the reinforcement has to be protected from the attack of the water, which contains chlorides and sulfates. When we ended up with designing with UHPC, we used in this case a hybrid structure. The 8 of the wall, 5 meter, did not allow us only to use fiber reinforcement. We scale it down to 15 centimeter thickness, or if you design slabs and buttresses, the thickness can go down to 10 centimeters. So it's true that mixed design is completely different, but it's also true that you use much less design. There is another important thing to take into account in the metrics. When you look at this mixed design, the steel fibers are already in the mix. So they count as a burden or as a cost voice for the cost per cubic meter of the material. When you have ordinary reinforced concrete, the reinforcement has to be taken separately, but you have to evaluate them both in order to have a complete thing. So we performed the life cycle analysis, and what we wanted to see, let's try to see how the performance of the structural bending moment, for example, capacity, decreases over time because of the aggression or is maintained because of the self-healing. So we use a different kind of aggression mechanism for chlorides. The fixed diffusion law governs the diffusion of the chlorides. When the chloride reaches critical content at the reinforcement, the corrosion starts, and depending on the scenario, you might have uniform corrosion or hemispherical pit corrosion. And we realized that, for example, for the ordinary reinforced concrete structures, you actually have a service life not of 50 years like it's estimated to be from the prescriptions, but you have something around 20 years, and this is critical. Other thing, the reinforcement starts corroding, and according to studies we found in the literature, when you have lost 20% of the cross-section, the pressure of the rust from inside is so high that you have formed 1 millimeter wide cracks. So you have to intervene because a wall with a crack 1 millimeter wide is no longer serviceable. And this was confirmed by the maintenance operations, extraordinary and unpredicted, that the company had to do. So this adds up to further burdens to your original CO2 and the original cost. When we designed it for UHPC, we employed the methodology in FIB model code, or ACI 544R. So you basically compute moment equilibrium with a stress blocking compression and a stress blocking tension. And what we did, we reduced the cross-section as long as the attack procedure. Very severe assumption in this case. But we said, let's start with that. So we embedded into the moment equations the Fick's law or other degradation laws. And we realized this. For example, surely the durability is extended, but also we realize that probably it's no longer the ultimate limit state which governs, but is the serviceability limit state, because you have slender structures which are more deformable. We said when the deflection reaches 10% of the thickness, it's already too much deformed, so you have to probably intervene. But still, in this case, for the slabs, we used the yield line analysis, because you have to design in two-dimensional way, and estimated the service life. Then we wanted to see, but this assumption of removing the attacked layer is too severe. The material probably is going to keep its performance. So we developed this setup to keep the material and the specimen under sustained loading while they were exposed to chlorides or to geothermal water or to tap water for comparison. And at the end of 1, 2, 3, 6 months and so on, we removed some of the specimens and tested them in bending or in direct tension. So it was a very huge experimental campaign, more than 2,000 specimens which were tested up to 1 year exposure, containing either alumina nanofibers or nanocellulose, and were investigated. And you can see here the capacity of the nanomaterials to keep the cracks narrower was confirmed. The reference material, you have 25 cracks, for example, in the range 10 to 20 microns. For the nano additional materials, this number is much higher. And most of all, what we observed was that after healing in the UHPC with nanomaterials, new cracks were formed and not the old ones were reopening, because the healing was so tough that it was easier to form a new crack. And you can also see here, compare the red one, which is the reference, with the black and the gray. The material with nanofibers was also able to maintain higher level of stress. So we identified this time evolving constitutive law of the materials. Obviously, we perform a test up to 1 year. You cannot go longer. Students have to graduate at a certain point. You have to allow them to finish. So we validated with numerical models to extrapolate this to the whole service life of the structure. So what we simply did is, when we computed the cross-sectional equilibrium for axial force and moment, we used time evolving constitutive laws. And we ended up estimating, you can see here, a service life longer than 100 years when we used our UHPC with nanomaterials. This is the case of the cantilever wall, and this is the case of the slab wall. Then you plug into your life cycle analysis software all the data that you need, and you end up showing that in the end, UHPC, different mixed compositions, different mechanism of aggression, is always more sustainable. This is just one indicator than the ordinary reinforced concrete solution. It's also interesting to see this. These yellow bars for ordinary reinforced concrete show negative. Actually, when you have to dispose steel, most of the life cycle analysis tools consider steel as completely recyclable, and so account for the negative account. They not consider concrete as recyclable, but we know that it is. So this is also something that we have to intervene, to work on, in order to have life cycle analysis tools that really consider all the potential benefits of this kind of materials. And when you end up costs, you see that the construction costs for ordinary reinforced concrete are absolutely comparable to the UHPC ones. It's true that the material costs more per cubic meter, but it's also true that you use half of it, 30% of it. So this makes the construction cost comparable. The huge saving that you have is that you do not have almost any significant maintenance cost, very limited, just to keep the structure functioning, and you do not have to intervene. So definitely, with this, I call it nano-functionalized UHPC, where we are really able to improve the durability, and we meant this as the capacity of the material to maintain the performance over time so that your structural performance does decrease. This material will help us in reaching the climate neutrality, circularity, sustainability objectives that we have always to work for. Just to thank the partners of this consortium, without which all this research could not have been done, and I also want to thank my research group, my family as well, which is here in this picture, and acknowledge the support of the funding institutions and companies. Thank you very much.